after the another. So the first one which we have here is bounded buffer problem, that is also known as producer consumer problem. So bounded buffer problem. So here what we actually have, like this one is also known as your producer consumer problem, and here what is actually going to be there. So we are like, let me just draw one diagram. So let us say we have here, from here we have your producer, and from here we will have the consumer. So that is how it is going to be there. So what will happen here, we are having a buffer of n slots, and every slot is storing some of the data there. All right, so what will happen here, you are going to be running two of the processes. One process you are running from the beginning, that is going to be your producer, and the another one which you are going to be running from the another one, and that is going to be your consumer. So what is actually going to happen, this producer will try to insert the data in the empty slot, and the consumer will try to remove it from the filled slot. So what will happen, as you are going to be like running both of these processes at the same time, so what will happen, whatever the output is going to be there, so that is not going to be as expected. So what we will be doing, we will be actually having a need where we will have to make the producer and consumer work in the independent manner, because here what is happening, they both are working together at the same time. So in such a case, what you can do, you can go ahead and use the semaphore which you have. So what the semaphore is going to be doing, so with the help of the semaphore, you can actually see that you are going to be synchronizing the flow for your producer and consumer, and because of that your entire thing is going to be well synchronized. Now let me show you the pseudocode for the same. All right, so here what we can do, we can just keep on running. So here what we will do, firstly we are going to be waiting until your empty is greater than 0, and once it is greater than 0, in such a case what you will be doing, you are going to be decrementing the empty. So we can say wait until your empty is greater than 0, and then decrement empty. All right, so what you will be doing, you are actually going to be performing wait there. So wait empty. All right, what is the next thing which you will be doing, you have to acquire a lock. How can you acquire a lock? By using wait. So wait on the mutex, you can acquire a lock. So the next one which you have is acquire lock. So you will be using wait on the mutex. All right, after that what you will have to do, you have to perform the insertion operation in a slot. So your next one is going to be perform insertion operation in a slot. So here what you will be doing, you are first going to be releasing the lock, and once you release the lock, you have to even increment the full. Okay, so the first one is going to be release lock. How you will be doing, on your signal you are going to be calling out for mutex, and after that the next step is going to be incrementing full. So how you can achieve it, you will be doing signal full. So based upon that you can actually have the problem which you can solve it in the best scenario. So here if you will see in this particular piece of code, so what we are actually doing, we can see that whatever the producer is here, so that is going to be waiting first of all. And for how long it is going to be waiting? Unless there is going to be one empty slot available. Once you have one empty slot available, after that we can just go ahead and perform the consumer one. So what we are actually doing, we are first of all waiting, and what it is actually going to do after that, it is going to be decrementing the empty semaphore. And how it is actually going to be helpful, because after that we are going to be having one less empty slot. So what your producer is going to do, it is going to be inserting the data in one of those slots. After that, once it acquires the locks on the buffer, so what is going to happen, the consumer cannot access the buffer until your producer is completing its operation. And after performing this insertion operation, we are going to be releasing the lock, and once your value is released, you are going to be updating the full. So what is going to happen, your producer will see that why we are actually going to be incrementing it, because your producer has actually filled a slot in your buffer. So that is your producer operation. Since we have separated it, so I'll just write down producer operation. After that, I'm going to be discussing about the consumer one. So for the consumer one, what we will be doing, first of all, we are going to be waiting unless your full is greater than 0. Once it is 0, after that you are going to be decrementing the full. Here I'm not writing the comments, just the pseudocode I'm writing. Okay, so do wait up to full. All right, after that what we will be doing, we have to acquire the lock. How can we acquire the lock? By using wait mutex. All right, after that we have to perform the remove operation. So we can say perform remove operation. All right, after that we have to release the lock. So how we can release? By using signal mutex. All right, later on you have to increment your empty. So what you will do, and here one more thing I have missed, that is while true. Till that it will keep on running. And here what we will be doing after that, you have to increment your empty, and this you will be running while this condition is true. So that is how you can actually go ahead and perform your consumer operation. And here what is actually happening, if I will show you this entire code, so what we are trying to be achieving here, if you will see, the consumer is actually going to be waiting unless you have one full slot available in your buffer. After that what it will do, it is going to be decrementing the full semaphore, because whatever your numbers of the slots were actually there, so those ones will get decremented by 1, and then your consumer can actually go ahead and complete its operation. So after that, if you will see what is actually happening, your consumer is acquiring the lock on that buffer. And if we are going to be following all of that, so you can see that whatever the consumer is going to be there, that is going to be completing the removal operation. And after that what will happen, whatever your data was there from one of your full slot, that is getting removed. So once it is getting removed, your consumer is going to be releasing the lock, and once it has released the lock, your empty semaphore is going to be incremented by 1, because your consumer has removed your data from that occupied slot, and then it also made it as empty. So that is how you can actually go ahead and perform your consumer operation. Now I'm going to be discussing about next one, that is your dining philosopher problem. So like we are mentioning about dining philosopher problem, so here what we will be having, we are going to be having some of the table, and here we are going to be having some of the philosophers who are just waiting for the food. All right, so here what is actually going to be there, we are going to be having 5 philosophers, and they are actually sitting around a circular dining table. So here we are going to be having 5 chopsticks and a bowl of rice that is going to be there. So let us say here we have your food, which is going to be kept in the middle. So what is going to happen at any instant? A philosopher can be either eating or thinking. So what we can do, when a philosopher who wants to eat, he will use two chopsticks, one from the left, one from the right. Let me draw the chopsticks as well. So let us say like this. We have kept some of the chopsticks. So what we are saying, if one philosopher is thinking at that particular time, he cannot eat. But if that person wants to eat, what it will do, it is going to be picking one chopstick from the left, one from the right, and he can eat. So in this particular one, what is actually happening, we can see that it is going to be taking a lot of, like, let us say some philosopher is thinking, so that philosopher can actually think for a very long time. But if a person is eating, he will have to stop at a time, so that time is going to be a finite one. So here what we have observed, that we are having the endless cycle of eating and thinking. All right, so here what we will be doing, we are going to be using the array of semaphore, and that particular one is going to be having, like, that array can actually mention it as stick 5, and based upon that we can actually go ahead and use the semaphore like solution here. So how it is actually going to be helpful? So when your philosopher who wants to eat the rice, he is going to be waiting for the chopsticks. He has to wait it from both of the sides. He will have to wait for the left as well as from the right. So what we can do, instead of doing that, what we will be doing, he will be waiting for the chopstick from his left, and what he will do, he is going to be picking it up, picking that one up. So after that, what he has to do, he has to wait for the right chopstick to be available, and then once it is available, he is going to be picking it up too. So after eating, what he will do, he is going to be putting both of the chopsticks down. But if, let us say, all the 5 philosophers are hungry simultaneously, then what will happen, everyone is going to be picking one chopstick from their left, right? So in such a case, a deadlock is going to happen, because nobody is going to be releasing their stick first. So if nobody is releasing, because they cannot eat from one, they can eat it only from the 2 only, right? So in such a case, it is going to be there in a deadlock for the forever. So what is going to be the possible solution for that? So sorry, yeah, so what is going to be the solution in such a case? So whatever the philosopher is going to be there, so that one is going to be picking up the chopstick only if both left and right are available. He cannot pick if only one is available. So in such a case, if both are going to be available, he can pick and he can start eating. And what we can do, like, this is one of the solution, but the another one can be there, that allow only 4 philosophers to sit at the table. So what will happen in such a case, if all the 4 philosophers pick up the 4 chopsticks, so there will be one chopstick which is going to be left. So any of the philosopher can start eating, and eventually, like, if somebody is eating, so we know that he can actually stop eating after a certain time. So in such a case, second philosopher can pick up the chopstick and he can eat. So in such a scenario, what we are actually achieving, we are avoiding the deadlock. So that is how your dining philosopher problem is going to be there. I'm not writing a lot because this video is actually getting a lot bigger. Now let us discuss about the second last problem, that is your reader writer's problem. All right, so in the reader writer's problem, what actually happened? In such a scenario, we are going to be having a shared resource which the other people can actually go ahead and use it. So here we are going to be having 2 types of processes in this particular context. So those ones we are referring as reader and writer. In this particular scenario, we can have any number of readers who can read from the shared resource, because, like I was mentioning, if you have a document, anyone can go and perform the reading, but only one can write. So we are providing read access to all and write access to one. So what will happen in such a case? No person can actually go ahead and write on that file. So what is going to happen when a writer is writing data to the resource in such a case? No other process can access the resource. But a writer cannot write to the resource if there are going to be non-zero number of readers who are accessing the resource at that particular time. This is what we are going to be ensuring here. So what is going to be the solution for the same? So in that particular scenario, what we can do, we can see that we are going to be having some of the readers. So we are going to be providing some of the priority to the readers. All right. So what we can say here, what like if we are not going to be considering that scenario, what is the by default scenario? We can see that your readers are having higher priority as compared to the writer. All right, so what we will do, if a writer wants to write down the resource, he will have to wait until no reader is currently accessing that resource. So what we will be doing, we are going to be using here mutex and the semaphore, and we are going to be using a variable which is going to be read count. So how that one is going to be helpful? So that one is going to be maintaining the number of the reader counts who are accessing the resource, and you're going to be having, and that particular your read count is actually going to be initialized to 0, and we are going to be giving a value of 1 initially to m and w. Okay, so here we have mutex m, to which we are giving value of 1. We have semaphore w, to which we are giving a value of 1, and we are having a variable which is read count, and to that particular one I am giving a value of 0. So here what we will be doing, instead of having the processes to acquire the lock on the shared resource, we are going to be using the mutex, and that particular one is going to be making this process to acquire and release lock whenever it is actually required for our read count variable. All right, in this particular one, what is the code which we are going to be using for the writer? So we can say writer process so that is going to be while true, and here we are going to be initially performing the wait, that one, and after that we have to perform the write operation. So then we are going to be calling out the signal on your semaphore. So that is how it is going to be working. Similarly, we can also go ahead and write down the code for our reader process. So I'm not writing down the code for the reader one. Those one you can go ahead and see from your slide. I'll just provide you the explanation for the same. So here what we will be observing, that we are having a writer, and what that writer is actually going to be doing. So that one is going to be waiting on your W semaphore, and for how long it is going to be waiting, unless it is getting the chance to write on the resource. After it is getting the chance to write on to perform the write operation, what it will do, it will be incrementing the W. So what the benefit of incrementing is going to happen? In such a case, we will know that next writer can come and they can go ahead and access the resource. Now, if you will go ahead and see the code for the reader, so in that particular one, what we are doing, we are acquiring the lock only when you are updating the read count. And when the reader wants to access any of the resource, so what we will be doing, we will be first of all incrementing the read count, and then we are going to be accessing the resource, and after that you also have to decrement your read count. So basically what we are achieving here, you can see you're going to be using the semaphore, which is going to be the first reader when it is going to be entering in your critical section, and the last reader which is going to be exiting the critical section. So the reason for that particular one, that why in that one, when the first reader is entering into the critical section, so your writer is going to be blocked from the resource, and only new reader can come and access the resource in such a scenario. All right, so that's all was there in this particular topic. I hope I was able to make it interesting for you. I